Welcome. Today is Wednesday, August 30th, 2017, and this is the Natural Hazards Engineering 101 webinar series. It is intended to provide a common knowledge base for the NERI community. For each of the primary natural hazards in the NERI program, webinars in this series provide an introduction to fundamental concepts and an overview of the experimental and simulation-based research. Webinars will also provide an introduction to numerical methods and computational tools used in natural hazards engineering research. For more information, visit the NERI website at designsafe-ci.org, where you can find links to the SimCenter and NERI Learning Center. Today's webinar is coordinated by the Natural Hazards Engineering Research Infrastructures Simulation and Computational Modeling Center. This webinar is supported by the National Science Foundation under awards 1612843, 1520817. Any statements in this webinar are those of the presenter and don't necessarily represent the views of the National Science Foundation. We are pleased to have Professor Ye from Oregon State University providing the overview of tsunami engineering. Professor Ye has academic and industry experience having worked in the area of hydrodynamics related to electrical power plants before returning to academia. His primary research interest is in the hydrodynamics of tsunamis, focusing on controlled laboratory experiments and theoretical developments of nonlinear long-wave theory. I invite Professor Ye to begin this introduction to tsunamis triggered by co-seismic fault rupture. Professor Ye?
Yep. Thank you for joining this webinar. I really appreciate for your time. The title of my talk is Understanding Tsunamis and Their Effects. See, how should I do this? Okay, that's fine. Okay, this photograph is taken the 11 months after the tsunami attack in town of Tomioka. It's very close to Fukushima Dai-ichi nuclear power plant. Even after 1 year, there's no recovery or nothing because of all the people are evacuated. So you can see the effects of the tsunami directly, even after 1 year. You can see that, all the pavements was ripped out, and the seawall was broken, especially the leeside of the seawalls. And so those are the effects of the tsunamis. This is a fishing port facility. What I'm going to do today is I'm going to try to characterize tsunamis with simple models. Of course, the tsunami is very complex, but simple model can at least give you some qualitative understandings. Of course, I cannot cover all of those for just one hour, but I'm going to try to choose maybe 2 or 3 topics that might benefit your effort for the modeling for the tsunamis and the evaluation of the tsunami effects on the man-made structures. The first things, let's try to talk about some dry facts. We really need to understand scale of the Earth when we talk about those large natural hazards. So that's why I'm going to try to explain this one first. Everybody knows about this, but we need to recognize, we need to have a real feeling about this. So radius of the Earth is about 6,400 kilometers. Okay, and then half of the radius is about core inside of the Earth. And then outside we have a mantle layer, which is about 3,000 kilometers. Well, if you add 3,000 and 3,400, that's 6,400 kilometers. It's all of those. So what I'm trying to say here is Earth's crust is 120 kilometers thick, atmosphere is 80 kilometers thick, oceans 4 kilometers thick. So ocean is very, very thin layer of the water, right? That's the way it is. And then it is also quite important to recognize that the horizontal scale of the Earth, actually on the surface, is much, much greater than the vertical scale. Right? So I think we got some kind of feeling about this scale on the Earth. Now, if I try to look at the more regional scale, there is we need to recognize that the depth of the ocean is 4,000 meters deep. So, it is difficult to make a greater than 4,000 meter wave because the entire depth is 4,000 meters. And then we have a continental rise and then continental slope. Those are sort of a range of that. And the variety of the width in the continental shelf, typically about 80 kilometers, sometimes much, very, very narrow, sometimes much wider. For instance, the East Coast is much wider than the West Coast of the United States. And then we have a coastal plain. So those are the sort of scale we need to recognize when we talk about tsunamis. So as an introduction, let me just quickly talk about the origin of the tsunamis. First things is we need to focus on the seismic fault displacement for the large earthquake. That's one thing. That's we're going to focus it today. Of course, tsunamis are also generated by large landslide and the volcanic eruptions. And very rarely, the tsunami can create a meteorite impact. Important part for this is landslide and volcanic eruption creates much shorter tsunamis compared to seismic fault. Let me just explain on this. Volcanic eruption, for that case, typical case is, well, I shouldn't say typical. The representative event was a Krakatoa, 1883. And then that creates the 40 meter of the wave. Lots of people died. But that indeed creates the huge tsunamis. But the island dimension is approximately 5 kilometers in diameter. So generated wave is just like that, like a 5 kilometer. And kilometer is the order of the magnitude of the generated waves. Okay. How about the landslide? Volcanic landslide and pyroclastic flow. This is similar to that they are volcanic eruptions. Famous one is 1793, Mount Mayu, Japan. That also creates pyroclastic flow. And that the picture of the pyroclastic flow is the left-hand side. And again, that the spatial scale of this event is about 4 kilometers wide, several kilometers. And then the landslides. This is a huge event for the 1958 Lituya Bay, Alaska. You can see that the splash up goes up to 524 meters high. It's probably this is the largest tsunami measured so far. But scale of that event is smaller. It's about 800 meters by 900 meters. So it's about order of the kilometers. So those are the tsunamis generated by landslides and eruptions and those kind of things. But if we talk about co-seismic fault displacement, which is much larger, the typical source area is 50 by 100 kilometers. Those are typical. What typical means like a significant tsunami is created by like a magnitude high 7s and low 8s. There's exceptions, of course. The 2004 Indian Ocean tsunamis, magnitude is greater than 9. The source area is 1,000 kilometers by 150 kilometers. 2011 East Japan tsunami is 450 kilometers by 150 kilometers. It's much larger than those caused by volcanic eruptions or landslides. This is important to recognize that those scale. So, what's the implication of the large source area? Hundreds of the kilometers in the ocean. So typical but significant tsunami is length scale of the wave is about 100 kilometers. And the ocean depth, typical ocean depth, abyssal plains, 4 kilometers. So ratio of the water depth to the wave length is 0.04, which is really small. Same thing for the 2004 and 2011 tsunamis, huge case. The ratio of the depth to the wavelength is really small. So that means this wave is qualified as long waves or shallow water waves. So at the same time, the tsunami amplitude in the open ocean is only a few meters. So if you compare with the depth, amplitude, ratio of the amplitude to the depth is really small. So all the tsunamis propagating in the open ocean can be approximated by linear long wave theory or shallow water wave theories. Okay? Now let's just try to feel what kind of length scale I'm talking about. This is 2004 Indian Ocean tsunamis, and I'm trying to indicate at the area of the Chennai area for here, and I plotted bathymetry. That the width of the continental shelf there is about 50 kilometers, and suddenly decreased about 3,500 meters deep. And then we do know that the wavelength of the 2004 Indian Ocean tsunamis, which is about 450 kilometers, which is satellite. So if I try to plot 450 kilometers, just like that. So it's much, much longer than the width of the continental shelf. Now, this sketch here is distorted. If I try to sketch one-on-one scale, vertical scale and the horizontal scale is same, then you're gonna get like that. It's very, very flat. So that's this tsunami for that. So if I say that, this is not a typical tsunamis. This sketch is not the typical tsunamis. Although I say it's a typical. Sometimes this is correct, sometimes not, but this is not the, you cannot fix the idea this is a tsunami waveform, all right? So let's talk about the run-up inundation part first. There's a variety of the tsunami form approaching the shore, which is quite important to model the tsunami effects on the shore. And on the shore means on the human beings, right? And so we do need to know what kind of tsunami forms it's approaching. If you're gonna do some kind of laboratory study for the structure and the infrastructure for tsunami hazards, we need to know what kind of waveform it is. Okay, this picture is taken in the 2011 Japan tsunami in Fukushima. And the tsunami form looks like a ball. The ball is a steep-fronted, very long waves. You can imagine that the wave has a step formations, and the front of the step is broken, so which is something like this in here. This is called ball. So this is one case, and people sort of look at this kind of waveform time to time from the Discovery Channel and those kind of things. And then there's some kind of variations. This is a formation of the angular ball. In an angular ball, is instead you have a turbulent front, you have a series of small waves behind that. This picture is taken 2004 Thailand. You can see that the boat in here, so you can see the scale on that. And initially, this wave looks like a dry down. So this looks like a leading depression wave followed by this angular ball is rushing onto the shore. This is a picture for 2011 Japan case and different locations in the Sendai plain. The series of waves coming. So this is sort of an angular ball start to break in front of the angular balls. if it's a very, very rare case, this is sort of a sketch. There's no photographs for that event. 1946 Eruption event. This looks like a wave breaking directly onto the shore and completely destroyed reinforced concrete structure, which is the lighthouse. This is very, very rare occasions. Usually, reinforced concrete structure is very strong and can withstand against the tsunamis, but this is the exceptions. I can show you more exceptions later on, which we found at the 2011 Japan tsunami case. Now, last formation is just like this. This is a picture in 1983, Japan Sea, Japan Sea tsunamis, I guess, yeah. Japan Sea tube tsunamis, I guess, 1983. You can look like this is gradual flooding. It's not breaking waves coming rushing to this. So you're going to get the variety of the form, tsunami form approaching to the shore. So which is not, you cannot uniquely identify the tsunami form in every locations. And then if you consider, variety of the tsunami, let's see something else on this. It depends on several factors. One of the factors is if the leading wave is depression means pulling the water, or leading elevation wave, which is pushing the water. We're going to talk about this effect later, very quickly. For the next slides. And then also bathymetry is quite important. And the broad continental shelf versus narrow continental shelf. Take a look at this sketch. If you have very, very long slope, like if this is, try to represent continental shelf and slope. If this length scale S of B is much greater than S of 0, then incident wave tends to break in the early stage because it takes a long time to propagate to the shore. Okay. On the other hand, if the wavelength is very, very long and the continental shelf is steep and narrow, then there is no time for this wave to deform. So you might be able to tends to have a gradual flooding for this case. So just simply sort of a characterize. And then, this wave might be amplified because of steep slope. You might be able to get a strong wave reflection to have amplifications. So, characterization of the waveform has depending on lots of factors, bathymetry, and also incoming waveforms. In order to know this, let's try to understand the generation first. Okay, I'm going to try to find the waveforms, right? How waveform changes. In order to understand the waveform, you have to understand how tsunamis is generated at the subduction zone. As most of people know, learned from the Discovery Channel and those kind of stuff, how tsunamis are generated. This is a typical case. Not always true. I should say typical. This is a simplified case. Oceanic plate is subducting underneath of the continental plate. And you're going to bring this one down. So gradually deformed down and lifting this. This process takes a long, long time, storing energy. And then suddenly this stored energy is released. And just pushing up, that creates the tsunami, and coming down in the shore. So that's the deformations. I'd like to emphasize that this is sort of a very simplified tsunami form, based upon the displacement of the seafloor. If you're gonna get the bouncing back, this is lifting up, right? At the same time, near the land, you're going to get the subsidence, right? And that gives you a lift, the negative displacement in here. So that determines incoming wave, if the incoming wave is leading depression wave or leading elevation wave. Let me explain. Okay, for that, if you have a subduction zone for this, let me just go. It's subducting like this, uplift and subsidence. The subduction for the 2004 Indian Ocean tsunami. This is a Sumatra, subducting this directions. Indeed, we predicted uplift in this side, east side, a subsidence in the east side, uplift in the west side, a subsidence in the east side. In 2011 East tsunami, subduction is from east to west. So displacement indeed creates the uplift in the east side, and that the subsidence in the west side. Just the support this hypothesis, right? So this is sort of a typical pattern for that the tsunami generation in the from the subduction zone. So let me ask, as a precursor of tsunami, the sea always recedes to the considerable distance. Well, if I think about this, that might be true, but I'll say not always. Let me explain to you. And can we predict when and where a tsunami forms the leading depression wave or receding waves? Maybe. Okay. Let's take a look at this. If this rupture occurs offshore, okay, just take a look at this. This is the initial ocean here. This is the coastal line, continental shelf, abyssal plain, continental slope in here. So if rupture occurs in the offshore, you're going to have this kind of pattern, right? Uplift in the offshore region, subsidence in the nearshore regions. So in this case, you're going to get the leading depression waves coming to the coastal lines, right? And the leading elevation wave is going outward. In this case, all of the co-seismic displacement takes place in the offshore. So for that, you're going to have, for this is a typical case, right? I mean, for that, this is a representative case for the ocean, Indian Ocean tsunamis. Uplift in this side, subsidence in this side. So for this case, if you examine the tidal gauge measuring at the Thailand is indeed shows that leading depression waves. And the tidal gauge shown in the India shows that the leading elevation wave. This complies with this model. All right? All right. So for that, in the leading depression wave, you shows that the huge bore formations. Because if you have a leading depression wave, wave front tends to become steepened much easier. So that's why for this, creating a bore formations. And on the other hand, on the picture, it's a flooding. It's a narrow continental shelf here. It's a very broad continental shelf here. If it's broad, wave tends to break, creates the bore formations. It's narrow, then leading elevation wave does not have a time to deform. So simply give you floodings. Now, if the earthquake happens and the displacement occurs near the shore, so for this case, this is the rupture area, all right? And then this is the deformation pattern for the black one. The red line is the wave relative to the shore elevations. Note that if this kind of displacement happened, shoreline also subside same time, right? So water displacement in relative to the shore location is just like that. Right? So for this case, it tends to have a leading elevation waves. I'd like to show it to you by emphasizing on that is whenever we have a displacement on the seafloor, and at the same time, the shoreline is also displaced. So this amount of the displacement of the ocean and the amount of the displacement at the land at the shoreline must be same. So there is no discontinuity in the elevation instantaneously. Right? That's important. So this is the subsidence. It's occurred at the Nicobar Island, 2004 Indian Ocean tsunamis. The lighthouse is submerged. It's a after the event, it's submerged on that. This is another thing in the Shikotan Island, 1994. This area, Shikotan Island, this subsided area, elevated area. So initial wave is elevation. Sorry. So initial wave relative to this is elevations, right? Slight subsidence in here. And then you can actually, tide gauge can show that the quantitatively shows that the subsidence. It's a 70 centimeter subsidence for this case from the wave gauge. Now, the last one is if the rupture really happened yet in the coastal line and including at the inland. This is February 2010 Chilean tsunamis. In this case, this is the displacement. So this is the shoreline. The shoreline is displaced up to here. So you're going to get the coastal uplift in Chile, right? So the initial waves clearly in the leading elevation waves. And so that in this case, coastal line uplifts at the same time. Sea surface at the shore also push up at the same amount. Right? So in this case, you're going to have a leading elevation waves. It should be different. If you take a look at this coastal line here for the Chile, you can see my arrow mark, I hope. Oops. So if you take a look at the shoreline, here's the uplift in here. All of those uplift. Here's a subsidence in here. So the uplift is red. The blue is subsidence. So all the tsunami tide gauge data shows initial wave to be elevation, except this guys. This must be affected by local bathymetry and topographies. Okay? Now, so this is the pattern. We talk about this. So for this, leading elevation and the leading depression wave, we talk about this. And the waveform is different. Bores, angular bores, the gradual floodings. Very rarely we have a direct wave breakings. All depending on the bathymetry on the continental shelf and the seafloor displacement pattern. And I have 4 bullets. Co-seismic sea level displacement relative to the land is that determines the leading depression wave and the leading elevation waves. And as I said, this is very simplified model. We have to recognize that there's exceptions. Some incoming wave might be grossly affected by local bathymetry and topography. So this may not be all the case, but in general, this is sort of a rule of thumb to think about this, right? The leading depression and leading elevation wave can be find out, how the co-seismic displacement relative to the land. And I also say that the ratio of the tsunami wave length and the length of the continental shelf is important. If the wavelength is very long, the continental shelf is very short, then wave simply reach to the shore without too much of the deformations, and vice versa. And the effects of the land uplift subsidence is very important for the modeling. Numerical modelings, we have to include this land uplift and subsidence. And sometimes if you have a land subsidence without taking into account, and they do tsunami models, and people sometimes claim that this is conservative. It may be so, but that creates lots of uncertainties. The reason for that is waveform itself changes. So it is very important if the land subsides and the uplift, we should take into account on that. The last spread is the one which I just talked about. Shoreline does not change instantaneously because the uplift occurs simultaneously in both the offshore sea bottom and the onshore ground. So I'm going to talk about the propagation for this. Why the 2004 Indian Ocean tsunami could travel across the Indian Ocean and beyond without significant attenuation. We also observed significant transoceanic tsunami effect 2010 Chile and 2011 East Japan tsunamis. Let's think about it. If tsunami has, okay, if you have a displacement in the sort of a localized circular shape, you might be able to say this is the model for the volcanic collapse, a landslide, or meteorite impacts. The wave attenuates 1 over square root r. R is at the the radial distance. So it attenuates very quickly. All right. So if you have a Krakatoa case, if you have collapse of that island, East Africa, wave, by the time wave reached to the other side of the Atlantic, say New York, the amplitude must decay very quickly because of the source is small, right? On the other hand, if you have a co-seismic fault rupture case, that the source area is very much elongated and very long and very large. So for this kind of source, we know that you're going to have a directivity for the energy propagations. And then this directivity is depending on the ratio, how elongated it is. The more the source of the elongation, the stronger the directivity. This is important things to think about. The distance. Distant tsunami means, that tsunami happened away from the area of interest. So this directivity, analytical model for directivity is, of course, you can show that in numerical model also. In the numerical model, they clearly shows the directivity for this. This is a 1960 Chile tsunamis hitting to Japan. Okay. And they we also need to recognize that the Earth is not flat. All right, it's a almost spherical shape. So any directed tsunami energy will propagate along the Great Circle. So from Chile to Japan, and then Alaska to San Francisco. This is a Great Circle. And distant tsunami source, okay, based upon this directivity and the Great Circle directions, I try to identify, which source will affect the U.S. West Coast. So right-hand side, this is sort of a chart which provided by USGS for the tsunami-genic faults in the Western Pacific and subduction zones. I look around this, and I can only identify 2 locations for tsunami, the fault direction. And if you push this one into the Great Circle and go into the West Coast, there's only 2 locations, nothing other place. You know, like a big rupture for the Japan case is not directing into the west coast of the US. That does not mean there's no effect. Of course, in 2011 case, there's small tsunamis in the west coast, but it's not in the direction of the Great Circle, aligned to perpendicular to the fault directions. Okay, but there's another location. In here it is. The Alaska is the one which creates, which points at the west coast of the United States. So if you think about the east end of the Eruption subduction zone, this directly hitting to the California. And this is probably most important source for the distant tsunamis. This might give you a significant tsunami effects on the west coast of the United States. And I should mention that because of this shoreline, you know, this elongation of the tsunami source can be doubled because of mirror effects. It can be a mirror effects in here. So this is a very important source. If you are interested in the distant tsunami, this is the primary candidate. Of course, there's another source, but this might be the most concerned for that, based upon that mechanism. For the summary, and we talk about length and time scale matters. And subduction zone and tsunami generation mechanism is important. We also talk about reading depression and elevation waves, coastal subsidence and uplift. And then elongated source gives you directivity and great circle. Those are the stuff we talk about in summary. I'm going to talk about very quickly the observation of the 2011 Japan tsunami. What kind of effects we got for geotechnical and structure issues? I'm going to just show just the 2 or 3 cases. It's not all. There are so much different kind of variety of the effects. One of those are upright, nearly vertical seawalls. Here is a Kirikiri, the vertical seawalls. Before, this is before, and then after. Okay. And this seawalls destroyed, and this all pieces pushed to the offshore world. So evidently this is broken during a drawdown. And this portion is scarred off. And you can see the car here, automobile. And it's flipped in this direction. So you can see the size of this concrete wall compared to this adult human beings. So that this failure is definitely created by that geotechnical issue, right? Foundation failure. And then I just need to sketch total failure by the scour in the front and back. And then just a few kilometers away, there's another town called Hakozaki. Very similar. But still, this is standing. But you can see from those 2 pictures, entire village is destroyed by the overtopping the seawalls. But in fact, this seawall is still standing. There's no damage. So there's a sketch. This is the existence of the flange. That makes difference. That's my guess, of course. But there's a difference for that. The existence of flange is that the difference between those 2 cases. How about mound-type sea dykes? Okay, you can see that front of the sea dykes is no damage at all. All the damage is in the lee side. Not only for that, lee side is top part, and then huge scour in the toe of the lee side. But front side is fine. Okay? So if I make a sketch, this is the damage on near the crown and the severe scar hole behind the dike. And then some Japanese calling this laboratory experiments, And this is the water surface for steady flow. We tried to make a measurements of pressure. It's a huge negative pressure in here, created by centrifugal force on that, and a large pressure force at the top, leeside, because water is flowing from left to right. So this shows something, the effects. How about extreme tsunami effects on the structures? This is the 2011 East Japan tsunami in Onagawa. Time to time, I show this sketch on these pictures. You can actually see this quite intriguing effects. There's a shadow zone for the strong building, and there is some kind of gap. That gap is creating huge flow, and this building is, it's fed by rotations. So the localized effect, variability of the local effect is significant for the tsunami run-up. This is another view for that. So this is a failure for the concrete structure. As I said at the very beginning, prior to this, the concrete structure was supposed to be very, very safe. Only exception was 1947 Eruption tsunami at the lighthouse. But this is just not only one. There's several of those. All those concrete structure fed by rotations. But structure itself might be okay. Simply this is flipped. And this is also dragged by 250 meters. A similar kind of building, this is still standing. This is 3 stories. I think this is 4 stories, I believe. And same locations. I show you. There's a one which is still standing. This is failed. And then, I don't have to speculate why these things happen, but looks like this has a very small amount of the windows. This is, all the windows are broken. So this is flooded by water. This wasn't. So the buoyancy force might be different. And then just the other day, August 21st, only a few days before, I revisited Onagawa. This is all flat. And they accumulate they put some kind of, they raise the ground level about by 10 meters or something like this. So it's completely different scenery, but no buildings. All the buildings was removed. Just for the comparison, if I compare with this. This picture is taken from here for this directions. Okay. So I just want to make a very short comment. It's very difficult to make accurate and quantitative predictions for extreme natural hazards. That's one thing. And the construction of the critical infrastructure buildings for true probable maximum loading may be economically impractical. Even it's practical, uncertainty involved is unknown or unreliable. Okay? We have to recognize that. So therefore, what we can do for the best is to cleverly tweak the design based on understanding of the physics, so that I call it the beyond the design basis events will not lead to the total disaster, but partial protection can be retained. So that's the sort of idea for this, some of the tsunami design. We always need to think about this. So last things, just very briefly talk about quite intriguing effect on this. This is pump station in Fukushima. Reinforced concrete structure. It's not failed by rotations. It's not failed by the foundations. Its structure itself was destroyed. This is very, very unusual. There's just 2 or 3 other cases we observed in the 2011 events. But this is one of the most severe case. Why these things happen? I do not know, but I can only speculate. Before and after, there is a protected by seawall. I can call the sea dykes. Here's it is. The sea dykes is but still standing, and huge amount of the scour. Because of this seawall or sea dike, incoming tsunami here can be stopped and then accumulate the water level. And then all of a sudden it's spilled over for the stored accumulated energy into this structure. That's my speculations. And then this sort of related to this type of that event. You try to store the energy, and then at the overtopping, that creates that huge release of the energy, even though this is still standing. Okay, that's my last talk, last slides. And if you have any questions, please ask me. I can try to give you some answers.
Thank you, Professor Ye, for this presentation. And at this time, we will open up the question and answer session. Attendees are reminded that questions should be submitted through the chat panel and sent directly to the moderator, and I will relay these to Professor Ye. And so we have a couple questions, Professor. And I think the first one is everyone is currently thinking about Houston and the devastating effects of storm surge and flooding due to Hurricane Harvey. And the question is, can we consider hurricane storm surge similar to the tsunami hazard?
It's yes or no. It's not identical, of course. Both storm surge and tsunamis can be considered as long waves. And storm surge is created by pushing the water on the continental shelf. So storm surge is totally rely on the continental shelf itself. And the effects of the storm surge is raising the water level, and then you're gonna have shorter wave created by wind forces. And tsunamis are a little bit different. Tsunamis are long waves coming from the offshore, rushing into the shore. Now, similarity on that is very severe case. Storm surge can create very similar surge of the water pounding onto the structure, just like a bore formations. It's a very rare case though, but I've seen such kind of stuff in the typhoon Haiyan. And I was also told, one of my colleagues, that this kind of phenomenon can observed in the Bay of Bengal, in that those kind of areas. So there's a similarity and that differences. A storm surge can be raise the water and pounding at the water, pounding by the wind waves. The wave itself is shorter than the tsunamis. The distinct difference is the effect of the tsunami can propagate across the ocean. The tsunami can bounce this one up and very, very long waves. And then that can create a effect on Japan, even though the source is in Chile. It's 17,000 miles away, 17,000 kilometers away. That is not the case for the storm surges. Storm surges created at the Houston, Texas, but there's not so much effect in Cuba, for instance. But it's similar kind of things happen for tsunamis. The Cuba is also great danger by this effect. So there's a similarity and the differences for both cases.
Okay. The next question touches on the seawall examples that you gave, where I guess one was broken and maybe one was not broken. And the question is, could one of the reasons be that one is in the open coast and the other is within a bay?
That's not the case. Both of those, the one I showed to you on those two events, is both are similar kind of locations. One of those, let's see, Kiri, you're talking about this. Oh, sorry about that. Oh, can we going back? Oh, no. Yeah. Sorry about that. Yeah, almost there. Here you go. This place, this is also in the bay. And this location is also at the bay. And then tsunami run-up height for this is 40 meters. This is a little bit greater, 70 meters. Both are overtopped. So I don't think this is the effect of the locations for this case. And the two locations are very close. I think the difference in that the damage for the seawall here is, I believe, that the structures, the design of this has a flange that makes different, prevent that the scour area. So that's why still this one is standing.
Okay. Another question is, what do we expect the leading tsunami waveform for the Cascadia event along the Washington and Oregon coasts?
I think this is a very interesting question, and I have to be very careful. But the continental shelf along the Washington and the Oregon coast is about 50 kilometers long. It's not really too wide. And then the co-seismic displacement must occur just like near the shore. So the leading wave is very likely in the elevation waves, leading elevation waves. I wonder if I can show this one. If I show this one, it's probably better. Here it is. Very likely for the Cascadia case in the Oregon and the Washington coast. It's just like this. Because we do know the coastal line is subsided by 1 to 2 meters for the period tsunami studies, for the geological evidence. So in that case, leading wave must be elevation waves. And I do know some of the numerical simulations. They also shows that the leading wave is elevation waves. But of course, since we do not have any history and observation of the wave itself, there's some kind of uncertainties. But from the simple-minded mechanism which I explained it to you today, indicates that the leading wave ought to be elevation.
Okay. A follow-up question to that is, what is the maximum probable run-up distance for a tsunami in the west coast of the United States?
Okay, run-up distance all depends on the slope, of course. If it's very, very flat, this depends on the period. So as far as the west coast is concerned, most of that area is sort of steep terrain. So distance-wise is sort of uncertain. In order of, if I penetrate 1 kilometer, that's sort of unusual. They might penetrate along the rivers for the much longer distance. But as far as run-up height is concerned, of course I do not know exact number, but most of the numerical simulation shows that order of the 10 meters.
Okay. And if we return to our focus to Hurricane Harvey, what lessons can the NERI community learn from this event in its approach to assessment or preparedness of the tsunami hazard on the built environment?
Yeah, both cases. It's it's not Hurricane Harvey. He behaved completely different from our expectations. He hit the Texas coast and came back to the Gulf and hitting again. This is not the way we understood for the behavior of the hurricanes. But that's the way it is. If you think about the extreme natural hazards, it's something unexpected things can happen. If you really think about the critical infrastructure and critical buildings, we need to consider such kind of stuff. However, we might not be able to design for everything just like that. So, you know, we have to make some kind of design guideline, try to make a design, you know, code to make something. That's fine. Even though you're going to get the critical structures, you have to have a design code. But at the same time, designer always have to think about something beyond. And you might be able to make some small changes, you know, small, not really obvious, but some very clever changes, design changes, might be able to reduce when the beyond design basis event happens. And this is the case for the Houston event, I guess. They make huge precipitations, right? I mean, rainfalls is unbelievable. And none of those drainage system was not designed. So that's what happened in the flooding, such kind of stuff. So for that, whenever you're gonna try to make a drainage system, you have to make some kind of design flood and those kind of stuff. But you can always think about, what if something beyond things happen? What can we do? You might be able to make some different kind of drainage system. You might be able to get just one system to relieve a little bit. I mean, those are just examples. And so same thing for the tsunamis. Tsunami is sort of unpredictable and not know when these things happen, rare event and high impact event. So you simply cannot design for that for everything. You just make small changes so that the structure or infrastructure can be resilient for those kind of events. For instance, the seawall can be overtopped. You know, try to design the seawall can be overtopped. But you know, try not to make a total destructions. Try to make a partial failure. Another thing is, you know, one of the building can be try to make some kind of failure so that they can be maintained standing, even though there's a partial failure. Those kind of idea is necessary, and not just for the design for the building itself. You may want to think about a regional design to cope with this kind of extreme natural hazards. That's my opinion.
Okay, well, we are at the conclusion of today's Natural Hazards Engineering 101 webinar. On behalf of the attendees, thank you, Professor Ye, for taking the time to share this introduction to the tsunami hazard. To the attendees, thank you for your participation and your questions. The NERI SimCenter is continuing its focus on hydrodynamic hazard engineering with additional NHE 101 webinars. The next webinar will focus on methods for modeling coastal waves with Professor Lynette from USC. Register for upcoming webinars on the Design Safe website and check your email inbox for registration links from announce@designsafe-ci. If you aren't receiving these emails, check your Design Safe account settings to make sure that you receive those announcements. Thank you for attending today's forum.